High in the Sierra Nevada mountains sits a physical record of a sudden, violent transition. These towering basalt columns at Devil's Postpile are the rigid geometric residue of cooling lava. 80,000 years ago, this was a uniform pool of liquid rock. As it cooled over thousands of years, internal tensile stresses grew until the uniform state destabilized. At a precise temperature threshold, the lava fractured instantly into this ordered hexagonal network. In dynamical systems theory, this is a symmetry-breaking bifurcation. It marks the exact moment a system reaches a threshold where its current state is no longer sustainable, forcing it to adopt a new configuration. Earth's entire climate system operates on these same nonlinear dynamics. It is an interconnected web of energy and matter governed by the laws of thermodynamics. Global warming follows the trajectory of a complex system being forced towards its own mathematical thresholds. Simple temperature tracking cannot capture the risk of the abrupt shifts ahead. Predicting our survival, our carrying capacity, requires us to understand the multivariable calculus that defines these planetary boundaries. We model the Earth system state as a sphere resting in a deep valley, a stable fixed point. But we apply pressure through a control parameter, the massive cumulative injection of CO2. This forcing shifts the system's underlying physics. As the control parameter increases, the valley floor rises and flattens, reaching a critical point where stability is lost. This occurs when the system's Jacobian matrix gains an eigenvalue with zero real part. The old state is destroyed, forcing a new equilibrium. Once this threshold is crossed, the system will irreversibly seek a new state, regardless of whether human intervention stops the initial forcing. A saddle node bifurcation occurs when two equilibria collide and annihilate each other. We are currently observing this in the Atlantic meridional overturning circulation. Rising freshwater input from melting ice acts as the control parameter, pushing the current toward an unstable threshold. If this fixed point is annihilated, the current collapses, permanently altering heat distribution across the entire northern hemisphere. Other systems undergo a hop bifurcation. Here, a stable fixed point loses stability and the system begins to vibrate between extremes in a continuous loop. We see this in the oscillating cycles of El Niño events, or the historical glacial periods that violently swing between ice ages and warm intervals. These mathematical phenomena are not abstract forecasts. They represent an active, measurable degradation in the stability of our current ocean and atmospheric currents. The same symmetry breaking found in basalt columns is occurring in Earth's planetary albedo, its ability to reflect incoming sunlight. Historically, Earth has maintained near-perfect hemispheric symmetry and reflectivity. Bright ice in the north was balanced by extensive cloud coverage in the south, keeping absorbed solar radiation equal between hemispheres. That symmetry is currently breaking. The northern hemisphere is darkening at roughly 0.04% per year as Arctic sea ice retreats and air quality regulations reduce bright aerosol pollution. This creates a hemispheric energy imbalance. As the north absorbs more heat, it pulls the intertropical convergence zone, the primary rain belt, toward the warmer hemisphere. Shifting the ITCZ reorganizes global monsoons. This forces massive droughts onto some land masses while flooding others, destabilizing historical weather patterns that human agriculture relies upon. A mathematical break in albedo symmetry fundamentally changes the circulation of the atmosphere, undermining the biophysical foundations of food security. The probability of triggering a bifurcation depends on the velocity of the forcing, how fast we inject energy into the Earth system. On the surface, land is heating 3 times faster than the ocean. But surface air temperature is only one part of the equation. The ocean absorbs 90% of excess heat, making mean ocean temperature the truest indicator of planetary imbalance. 20,000 years ago, the ocean water column warmed at roughly a quarter degree per 1,000 years. Today, that rate is 8 to 10 times higher. Applying this velocity to the planet's primary control parameter ensures we will hit critical eigenvalues faster than the biosphere can adapt. Global policy often treats the climate as a secondary concern to economic growth, but the mathematics of carrying capacity suggest these two goals are in direct conflict. This equation defines global carrying capacity, the maximum population Earth can sustain at a specific welfare level. It has two strict conditions. The Earth system state must remain within the biosphere's safe operating space, and its rate of change cannot be negative. Human culture functions as an external metabolic system. Our expansion, the land we transform and the energy we consume, is the physical manifestation of the control parameter forcing the Earth system. We are filling natural waste sinks faster than they can drain. This is the state of overshoot. By exploiting the ecosphere beyond its regenerative capacity to maintain material growth, we are effectively attempting to wager against the second law of thermodynamics. Because Earth is a coupled nonlinear system, avoiding critical eigenvalues requires a reduction in the economic throughput that drives the forcing. Without a coordinated contraction of that throughput, the planet's dynamical thresholds will enforce a brutal physical